I want you to focus on your TA Indy and on this one single dot. Today I'm going to help you solve a fluid mechanics linear momentum problem with a stationary control volume that is a pipe bend, right? A pipe elbow. Now your textbook probably has some variation of the Reynolds transport theorem, which when applied to fluid momentum is one of the most stupidly overly complex equations you'll see in your entire undergraduate career. But we're only going to use this dot. This is the Reynolds transport theorem, but this is your TA Indy's dot. I mean, look at him back here on his hamster wheel. It's in the shape of a dot. And if you can just remember this one dot, then you don't have to use this equation at all. And the only main equation you're gonna need is regular plain old Newton's second law, F equals ma. I'll get to Indy's dot later, but starting from the beginning, first step is always gonna be to draw the control volume. This is gonna be a dashed line around your drawing that encompasses all the important parts. And the one thing you really need to make sure of is that your control volume is perpendicular to the direction of flow. So don't just draw a box that includes the shape. Make sure that your box has all of the weird little corners and things necessary so that anytime flow enters or leaves your control volume, it leaves it like perpendicular. And that has to do with Indy's dot, but we'll come back to that later. So I wasn't lying when I said F equals ma is the main equation you're gonna use, and that's really all you're gonna need for this. You're gonna set this up just like a problem from back when you took regular dynamics, back probably your sophomore year. F equals ma means a free body diagram, which has all of your forces, is equal to your kinetic diagram, which has all of your changes in momentum. So on the free body diagram side, your forces, we've got weight of the actual metal that makes up the pipe elbow, weight that contains all of the water contained within the pipe elbow, which is actually way heavier than the metal itself. And the thing that a lot of students would forget for this problem would be that they need to include pressure. So all around the entire control volume, atmospheric pressure is pushing in from every direction, except for this one tiny section where the inlets and outlets are. Since this fluid system is pressurized at that one little cross-sectional area at the inlet and the outlet, the control volume is exposed to higher pressure than atmospheric pressure. Since we were given this problem that both the inlet and outlet have a gauge pressure, which is going to be above atmospheric. So if pressure is force divided by area, then force is pressure times area. So the pressure of the water on the inlet is pushing the system to the right. And so even though water is flowing out of the outlet, the pressure at the outlet is still pushing upwards into the control volume because pressure pushes right in every direction. And the last forces are just going to be a combined sort of Fx and Fz pointing horizontally and upwards that account for all of the different bolts that are holding this flange in place. If this were a mechanics course, we'd probably include forces actually for each individual bolt, both at the flange at the inlet and the flange at the outlet. But since this is a fluids class, we're just interested in sort of the overall sum of all of the forces supplied by all of those bolts, so we can just put a generic horizontal and vertical force that includes the effect of all of them. So next, the kinetic diagram, which accounts for all of the changes in momentum. So linear momentum is mass times velocity. So to find the rate of change of momentum, we can either take the derivative of velocity and get acceleration, right? That's ma, which for this problem is 0. Or we can take the time derivative of mass and get mass flow rate. So m dot v is how we account for the fluid flowing into the system and out of the system, right? Both ma and m dot v are both accounting for the change in momentum of the control volume. And this is it, the free body diagram and the kinetic diagram, all of your forces on one side, and then all of your ma and your m dot v on the other side. That's all you need for every momentum problem you'll see in this class, whether it's stationary control volume, moving control volume, accelerating control volume. You can do all of that with just F equals ma, just these two diagrams. You don't need the whole giant integrals of the Reynolds transport theorem, right? They're all included in these diagrams, mostly. As long as you're making the steady state assumption. That's actually the one thing that these diagrams don't account for right now, but everything else is included. All right then, well, let's just write out the equilibrium equation then. We've got all of the forces on one side, and we've got our m dot v and ma terms on the other side. We'll write two equations, one in the x direction and one in the z direction. And I'm calling the vertical direction z instead of y, just because that's generally how we do it in fluids. It doesn't really matter if you want to call it y, you do you. All right, and now it's the moment you've been waiting for, your chance to learn from your TA Indy, what the heck is his dot? Why was that so important? And the reason is to remember the sign convention. Over on your kinetic diagram, m.1v looks like it's pointed to the right, so you want to call that a positive term. But in the Reynolds transport theorem, that dot stands for dot product, right? When you have two vectors, a and b, with an angle theta in between them, the dot product is ab cosine theta. So fluid momentum is not just m dot times v. So mass flow rate is density times velocity times cross-sectional area, right? With velocity and cross-sectional area is essentially volumetric flow rate. Well, in the Reynolds transport theorem, it's not just v times a. It's not just velocity times area. It's velocity dot area. It's a dot product. And if velocity and area are not pointing in the same direction, then you have to include an angle. And so what this dot is there to remind you for, the why that you need to remember Indy's dot is because the area vector points outward from the control volume. So if your fluid flow is pointed outwards, it will be going the same direction then as the area. And so your angle in between them will be 0, and cosine of 0 is 1. It was a very long, complicated way for me to say that fluid leaving the control volume will be positive, which is totally bizarre and unintuitive. If you did not account for Indy's dot, you would almost definitely want to say that fluid either pointing to the right or that entering the system should be a positive term. But no, your m dot term is going to be positive if it is leaving the control volume, because that's the same direction as the area of the control volume. So m.1 is entering the control volume. This means that there's a 180-degree angle between the area of the control volume and the velocity of the water at point 1. And cosine of 180 is -1, which makes that mass flow rate entering the system negative. This is also why at the beginning of the video I said it was vitally important to draw your control volume perpendicular to the flow. This will ensure that your angles are either 0 or 180, so either +1 or -1 for the cosine term. All right, so circling all the way around back to our problem here, as I write out my m dot v terms, my m dot term is negative if it's entering the control volume, because it's opposite the direction of area, and my m dot term is positive if it's leaving the control volume, because it's going the same direction as my area vector. The velocity term is positive if it's pointing to the right. The velocity term is negative if it's pointing to the left. And I will always write this in or out or right or left next to all of my signs for these problems, because making a sign error is so easy to do. Even if I remember to account for the Indy's dot and the direction of the area vector, there's still like a decent chance that I'm gonna mess up a sign. So I put these little notes next to it just as a reminder so that it makes it easy to catch a mistake later on if I see that I made a mistake. So z direction equation on the sum of the forces side, right? I've got a pressure force at the exit that's kind of pushing diagonally upwards. I've got two weight vectors pointing down, and then my z vector, that's the reaction force that I'm trying to find, which I've drawn as upwards. Over on the right-hand side, the inlet is purely horizontal, so it won't appear in this equation at all. Only the exit has a vertical component. And since the exit flow is leaving the control volume, that means velocity is in the same direction as area, so Indy's dot will make that term positive. And then the velocity vector is pointing downwards. So downwards will be negative, so the velocity term is gonna be v sine 45, but negative because it's pointing down. All right, and with that, we've basically done all of the engineering for this problem. Now we're just trying to little like plug and chug, just fill all the numbers in and solve for F. So the weight vector is gonna be mass times gravity, right, for the weight of the metal. Since we were given volume for the weight of the water, it's rho times volume times gravity, right? With density converts the volume back into mass. We're gonna need areas for both the inlet and the outlet. The inlet was 400 millimeters, 0.4 meters. The exit, 200 millimeters, 0.2 meters. We're gonna need velocities at the inlet and the exit. We're given volumetric flow rate, and Q is V times A. And we're also gonna need mass flow rate. So since we were given volumetric flow rate, we can just multiply that by density and get the mass flow rate. We weren't actually given density for this problem, or temperature, so I can't even really look it up in a table, so I just have to make an assumption, and I'm gonna assume the easiest possible number, which would just be 1,000 kilograms per meters cubed, to make all the math as easy as possible. And I don't need to solve for multiple mass flow rates because based on the continuity equation, if this is a steady state problem with no accumulation within the elbow itself, then the mass flow rate in will equal the mass flow rate out, right? There's only one inlet and one exit. So let's start plugging back into the equilibrium equation. 150 kilopascals needs to get converted back into pascals to make sure all the units are going to cancel. For pressure 2 times A2, don't forget the cosine 45 degrees because that pressure is pointing kind of upwards at an angle. It's not purely to the right like pressure 1 was. And then you'll see Indy hopped back on his hamster wheel back here, right? Indy's dot to help us out with the sign convention. Since m.1 times v is going into the system, m.1 is negative, right? And v is positive because it's pointing to the right, right? We can completely ignore the ma term, right? Because acceleration was 0. This is a stationary control volume. And for m.2 v2, right? Indy's dot says area is pointed outwards. So since mass flow rate is outwards at the exit, m.2 is a positive term, but the velocity is pointing to the left. So the velocity term is negative. So combined, this term will end up being subtracted. There is a cosine 45 degree term in here, but that cosine is because the fluid is not pointing purely to the left. It's kind of at an angle to the left. Do some calculator work, 25.7 kilonewtons as a force in the x direction. And note that I got a positive answer here, but on my free body diagram, that is a force pushing to the left. The strongest term in this equation is actually pressure at the inlet. There's a very high pressure pushing to the right. And if the bolts weren't strong enough, it would actually just like blast the elbow off to the right. So the force is mainly pushing back to the left. So I chose the correct direction for my Fx at the beginning of the problem, pushing back to the left. Same thing now to find Fz using our second equilibrium equation. Plug in pressure, area, and this time sine of 45 degrees because now pressure is pushing partially upwards. Subtract the two weights. Over on the right-hand side, we can ignore the mass flow rate due to the inlet because it's only horizontal, so we're only accounting for the mass flow rate through the outlet. The m dot term itself is positive because it's leaving, but the velocity term is pointed downwards, which is why this whole term is still negative in total. And this time, sine 45 degrees to get the vertical downward component of velocity. Some calculator work gives me negative 3.5 kilonewtons. And this negative means that my initial arrow that I drew on my free body diagram, I guessed the wrong direction. The force is actually pushing downwards, which is really saying that even though the weight of the water is pushing down, the pressure pushing upwards is actually even stronger than the weight of the water. And so the bolts attached to the flanges are actually holding the pipe downwards a little bit. So look how comfortable your TA Indy is back there on his hamster wheel, right? Just chilling with his dot. If you can be as comfortable with the dot in the Reynolds transport equation, you can forget the entire rest of the equation. Just try to be as comfortable with that dot as Indy is with his hamster wheel. And that will ensure that you always get the sign convention correct on all of your momentum problems. And that's going to make these problems way easier than they otherwise would be. Next video up on the screen, another momentum problem, but this time with a moving control volume. It's mostly the same, but just a little bit different because your velocities will need to be converted into relative velocities since the control volume is moving.